Hello, good morning, good afternoon, or good evening, whatever time you're watching this video. It has been a while since I planned to upload a video. Is this video is helpful for those who wanted to review the concept regarding Kepler's planetary motion. So I have three problems here, but before that, we will have to revisit the three laws of Johannes Kepler regarding planetary motion. But before that, we will have to revisit first the three laws of planetary motion. The first one, we have the law of orbits, or it is also called elliptical law. It says that planets move around the sun in an ellipse with sun as the focus, one of the foci. Okay, and then we have planetary paths are not perfect circles, but they are stretched ovals, making it look like an ellipse. If you wanna draw a perfect ellipse, you can have, you know, two push pins, have it end to end, and then you will have a yarn, knotted yarn, and then you have to place your pen there and try to stretch out like you're you're making a shape. It will finally um, arrive, or you can draw the perfect ellipse. And we have the law of areas. That's the second law of planetary motion. It is called the equal area law. That's the North Star there. The equal area. Whatever swept out during the motion of the planet from position one to position two, the area being swept out is equal. Yeah, it's equal. And then planets moves faster when it's closer to sun, and then it's slower when farther to the sun. Okay, and when the planets or any celestial body is closer to that big star or to that sun, we call that one perihelion. And then on the other hand, the planets far farther from the sun, we call that aphelion. And the law of periods, or it's the harmonic motion law, the square of the square of a planet's orbital period, the time it will complete one orbit, or t squared. The square of the planet's orbital period, t squared, is proportional to the cube of the semi-major axis of its orbit, or that's R3, radius cube, the cube of the semi-major axis. That's the radius of its orbit. Planets that are farther from the sun take much long time to complete one revolution. We can connect that one to the aphelion, that a aphelion phenomenon. When it's far away from the sun, it moves slower, so it will take more time, or much time, or a high period before it can complete one orbit or revolution. All right, so let's have this ellipse. That's the ellipse, like a stretch circle forming oblong. And at aphelion, this is the sun, and the black dot or circle will be represented as the planet. At aphelion, it's far away from the sun, so it will move very slow. It will move slowly. So we have it here a short arc A very short, let's say in linear motion, is a very short displacement because the planet moves slower this time. Okay, and remember the area here, area, let's say this is area 1, it is equivalent to area 2 according to the second law. Whatever being swept out from the odd, but yeah, according to the second law, these two areas are equal. Okay. And during perihelion, the sun, I mean, the planet is closer to the sun, so it will move faster, creating larger arc. In linear motion, it will create. If we will put this arc into a line, it looks longer than the line being formed here at aphelion. Right. So problem A planet is 200 million kilometer from the sun at one point of its orbit and revolves at 25 kilometer per second and 90 million at another. Figure out the speed at a point where a planet is near the sun. So if you notice here, we have like a distance from the sun, 200 million kilometer, and we will compare that one to 900 million. It is, of course, kilometer to have consistency in the problem. So obviously, 200 million kilometer is longer distance from the sun. So this is our aphelion for sure. And we have 90 million kilometer distance from the sun. That's our perihelion. So the planet will move faster in this point or position. Let's figure out the speed at where a planet is near the sun. So probably it's 90 million kilometer. This is closer to the sun compared to 200 million kilometer. By the way, the speed of our planet at 200 million kilometer, it's 25 kilometer per second. So we will be expecting that the velocity at 9 million kilometer will be faster than 25 kilometer per second. We have given variables here. Radius 1 or the distance 1 will be, let's say it's the 200 million kilometer from the sun. And we have the velocity of that radius or distance, that's 25 kilometer per second. R2 will be then the other distance mentioned in the problem when a planet is now closer to the sun. So it's 90 million kilometer from the sun. And then we have the velocity to that unknown velocity that we will try to solve. Okay, so the formula, if in deriving to the answer of the velocity at aphelion, we have um, R1 V1 is equal to R2 V2. So we will just substitute all the variables in the problem. R1, remember, it's 200 meter kilometers, so we will gonna substitute it here in R1. 25 kilometer, that's the velocity at radius 1. We have V1 here, we can put that one in there. And then we have 90 million kilometer. Sorry, this is gonna be the um. Hold on. This is gonna be the value, or yeah, the value of our art, and then our unknown will be v2, the speed at 90 million kilometer. So upon substituting all the units correctly in the formula, so we can have it here, 200 200 million kilometer, and then 25 kilometer per second multiplied these two factors is equal to 90 million kilometer multiplied by the unknown velocity 2. Next is we will have to divide both sides by 90 million kilometer in both equation to cancel out this one. And we can isolate the v, cancel, and then you will multiply first 200 million kilometer and 25 kilometer per second before you will divide it by 90. Cancel, then you will have it this way. It's the standard number here. And we have 5 times 10 raised to 9 kilometer squared per second. And then we will divide it by 90 million. We can cancel out 1 kilometer here. So we will have 1 kilometer. Okay. And yeah, once you canceled this unit, you can have a remaining unit of kilometer per second, 55.56 kilometer per second. That's the speed of a planet when it's 90 million kilometer away, or yeah, away from the sun. Actually, it's closer compared to 200 million kilometer from the sun at one point. So yeah, as we expected, from 25 kilometer, when it's very far from the sun, so it will gonna move slower at 25 kilometer per second. But when that planet is now nearer to the sun, so it will gonna speed up to 55.56 kilometer per second. It takes 55.56 kilometer per second to orbit the sun at that particular radius or distance. So we have problem B. A planet sweeps out an area of 5 times 10 raised to 10 kilometer in 10 days. Figure out the number of days to sweep out 1.5 times 10 raised to 11 kilometers squared. This will gonna be the area, and in 10-day area, it will be swept in 10 days. And we need to find the number of days in this new area. Okay? Given we have area 1B, the area swept in 10 days, so this will gonna be the area 1. And then the period in days, not in seconds, it's in 10 days. We have the area 2 here, 1.5 times 10 raised to 11 kilometers squared. And then we need to find the number of days. We can use this formula, A1 over A2, period 1 over period 2, in days, not in seconds. So you will substitute A1, and then we have 10 days here for our period, and A2, 1.5 times 10 raised to 11, and we do not have T2. So we need to find T2 here. Let's substitute. And it must be squared because we're not dealing with volume here. It is area. So we can have 2 in that case. Next thing we have to do is to cross multiply. 5 times 10 kilometer squared times T2, and then we have 1.5 times 10 um, raised to 11 kilometers squared times 10 days. So we can have this equation here. 5 times 10 raised to 10 kilometer squared times T2, and then 1.5 times 10 kilometers squared times 10 days. This one. First things first, we have to multiply these two factors here before we will divide it by this magnitude. Okay, we will divide both sides by 5 times 10 raised to 10 kilometers squared, and we can cancel same magnitudes or units in this equation. So we can cancel out the following: 5 times 10 kilometers squared cancelled, and the units kilometers squared will be cancelled also. Now you can multiply 1.5 times 10 raised to 11 by 10, and then divide it by 5 times 10 raised to 10. So after you multiplied 1.5 times 10 raised to 11 by 10 days, you can have 1.5 times 10, 12 raised to 12 days, divided by 5 times 10 raised to 10. So you can have a period in days, 30 days. So it will take 30 days to sweep out area of 1.5 times 10 raised to 11 kilometers squared. That's it for problem B. I have here the last problem. It's problem C. At perihelion, Earth is 147 times 10 raised to 6 kilometer from the sun. Perihelion, that's near from the sun. Okay. And at aphelion, it is 152 times 10 raised to 6 kilometer. If Earth's speed at aphelion is 29.3 kilometer per second, let's figure out the speed at perihelion. Same as our problem A, but this time it has a specific like term used here, perihelion and aphelion. So we will be expecting at perihelion, it will gonna speed up faster than 29.3 kilometer per second. So let's have our given RA. RA stands for radius at aphelion. So you have A here for aphelion. I forgot to put letter P in aphelion. And we have velocity at aphelion. A is not acceleration here, it's aphelion. So um, velocity at aphelion, be the speed at aphelion. That's 29.3. My slide is very inconsistent this time, my apology. And then you have the RP. That's the radius at perihelion. Okay, and then we have the velocity at perihelion. We can still have that equations like before, like in problem A. RA radius at aphelion multiplied by the velocity at aphelion, and then radius at perihelion multiplied by the velocity at perihelion that we need to figure out. Let's substitute it correctly so we can have this value. This is the value of RA, and it's going to be the value of 2VA. And this is the value of our radius at perihelion, and we do not have the VP. Let's continue. You have to multiply, you have to multiply this factors here before you will multiply it by 147. Okay, so we will divide both side by 147 times 10 raised to 6, and then multiply first the figures in the numerator before you will divide it. Okay, cancel. So you will have this product of 4.4536 times 10 raised to 9 kilometers squared per second. That's the product of this factors here. Then you will divide it by 147 times 10 raised to 6. So you will have a speed at perihelion that's 30.30 kilometer per second. It's greater, um, just not so great, but yeah, it's greater than 29.3 because it's now nearer to the sun. Okay, anyway, their distance is not that far. 147 times 10 raised to 6 and 152 times 10 raised to 6. So we can have this increment of 30.30 kilometer per second. Thank you for watching, and I hope you learned something from today's video. Thank you so much and see you until next time. Bye for now.